Okay, so we're still in section 4.5. We got to finish that one, and then we'll do 4.6. So let's just start with an example. Consider a function. Where's my example? Two x plus 3 over 3x squared plus 7x minus 6. Okay? So first, let's just go through the motions. First, we want to find the x-intercepts and y-intercepts. So how would you go about finding the x-intercepts? What do we need to do? Yeah, or in this case, just set the numerator equal to 0. That's what we agreed usually works. Whatever turns numerator to 0 will make the entire function equal 0. So solving for x, you get x equals negative 3/2. So that's the x-intercept. The y-intercept will set x equal to 0. And if you do that, you'll just end up with whatever that ratio is. So it will be y equals negative 3 over 6 or negative 1/2. Yeah, so that you do this for any function, not just the rational function. You're finding the x and y intercepts the same way, no matter what the function is. So as an ordered pair, the x-intercept is negative 3/2, 0, and the y-intercept is 0, negative 1/2, if you want to think of that as an ordered pair. So we can actually start sketching this thing. So negative 1/2 somewhere here on the y, and negative 3/2 is somewhere there. So we have this x-intercept and that y-intercept. Right? It was negative 1/2, I think. That's what we found. Right? Okay. Is that all right? Finding asymptotes. So vertical asymptotes is basically looking at the denominator. We'll have to do some factoring, right? So basically we have to solve for the denominator, find the zeros of the denominator. So we can probably factor that, or we can use the quadratic formula. Now remember how we factor these types of problems. We'll multiply the first and the last, the leading coefficient with the constant term. So what is that product? Only negative 18. Negative 18, and we're also going to look at the number in the middle. So can you find two numbers that multiply to negative 18 and add to 7? What are they? 9 and negative 2, right? So numbers that multiply, so that's the product. And this is the sum. So the numbers that multiply to negative 18 and add to 7 are 9 and negative 2. So what we do in this case, we'll split the middle term as the sum of 9 and negative 2, right? And then we'll just factor by grouping, right? This is the old school factoring. So the first two terms, I can pull out a 3x. The last two terms, I can pull out a negative 2, right? And then you pull out x plus 3, and then we're done factoring. I mean, you could use the quadratic formula, of course, to solve this equation, but if you factor, then you can see that x equals negative 3, and you solve that one, x equals 2/3. Is that okay? Again, if you cannot, I mean, you should be able to factor these, but if you're stuck on factoring, use the quadratic formula. So this will be the equations of our vertical asymptote, so negative 3. So we have a vertical asymptote at negative 3. And 2/3. So if this is 1, 2/3 is somewhere here. So these are our vertical asymptotes. Is that okay? Now horizontal asymptotes, well, let's do them here. So if you look at our function, it had a linear numerator and quadratic denominator. So the degree of the numerator is 1, degree of the denominator is 2, so denominator is bigger. So what is the horizontal asymptote? 0, right? So since the degree of the denominator is greater than the degree of the numerator, then the x-axis would be our asymptote. Is that okay? All right. Well, now we just need to connect the dots. And every time your x-axis plays the role of an asymptote, it's always confusing whether you're going above or below the asymptote. So in this case, we can pick a number and plug it in just to see whether we're above or below the x-axis, because we don't really know. I mean, we can make some assumptions that most likely, actually, let's make some assumptions, okay? Because I think we discussed that at the end of last class, that we can use that idea of multiplicity here, okay? So the sign of the function has to change around the asymptotes or zeros of odd multiplicity. So if you think about this, if you try to connect Was that an just had to find out, otherwise it would just be amazing. All right, I want to do one more example of those rational functions, and then I'll teach section 4.6 in probably one sentence. Well, two sentences. So let's do this example. Again, just trying to sketch the graph of a function. Negative 2x squared minus x plus 15 over x squared minus x minus 12. It is always a good idea to try and factor first, because if things factor nicely, then the rest of the problem becomes a lot easier. We can actually do some factoring here. And the way you want to do the factoring, if you have a polynomial that starts with a negative, like here, then pull out a negative first. So it's plus x minus 15. Over denominator is really easy to factor, x minus 4, x plus 3. Right? Now, to factor that numerator, we can still do that process where we multiply 2 by negative 15. So that's negative 30. And then you need numbers that add to 1, so that's 6 and negative 5. But a lot of times you can just kind of guess the way it factors. And in this case, let's try and guess. Let me show you how you guess. Because when you start with a 2, then the only options are 2x and x. There's no other way to get 2x squared, right? Now to get negative 15, probably going to be 5 and a 3, depending on the sign, right? Now we just have to play around. So we agree, right? 5 and 3 both opposite signs, negative 5 or positive 3, negative 5. And since the middle is positive, probably the bigger number is going to be positive, so probably it's going to be negative 3 and positive 5. All right? Now just the only question is where to put it, because you can put plus 3 minus 5 like that, right? So if you FOIL, you get what? 3x minus 10x, right? So your middle is 10x, negative 10x, and a 3x, so it's negative 7x in the middle. We only have x in the middle, so that's not going to work. So what I'm doing, I'm just checking the middle term. So let's flip them around. What if I put negative 5 and a positive 3 like that? Then the middle term is this product, which is 6x, right? And that product, which is negative 5x. So what do they add up to? 1. That's what we want, right? So that's how you factor that one. 2x minus 5, and then x plus 3. Or you can use that other technique. So they both work. I mean, sometimes you can just guess your factoring, right? What is the domain of this function, by the way? That's right. So domain would be all real numbers except for 4 and negative 3. Although I can do that, right? X plus 3, they cancel. That does not affect the domain. Remember we talked about that. Even if you can reduce, will not affect the domain. So my function now is really negative 2x minus 5 over x minus 4. Right? But still, negative 3 is not in the domain of our function, so we'll have a hole in the graph at negative 3. But now we can continue with the rest of sketching this thing. So finding the x-intercepts. So we're just going to set numerator equal to 0. 2x minus 5 equals 0, solve for x. X equals 5 halves. Right? That's the x-intercept. The y-intercept, set x equal to 0. So what are we left with? Just negative 5/4, right? If you set x equal to 0, you get negative 5 over negative 4 with a negative up front. So we'll get y equals negative 5/4. So again, I can start sketching this thing. So we have, what was the x-intercept? Positive 5/2, so somewhere here, right? The y-intercept is negative 5/4, so it's 1 1/4, so somewhere there, right? Okay. Asymptotes. Do we have any vertical asymptotes? What are they? Vertical. Just 4. Because remember, the vertical asymptotes is after you reduce. Okay? So negative 3 is still not in the domain, but the vertical asymptote is only 4. What will happen at negative 3? You're going to have two lines approaching each other with a kind of hole in the middle. So it's not going to have an asymptotic behavior. Nothing's going to be flying off. So the only one vertical asymptote is x equals 4. Now, horizontal asymptote, as you just said, was negative 2. Is everybody okay with negative 2 for horizontal? If you look at the original one, it's negative 2 over 1. If you look at the simplified one, it's 2 over 1, but there's still a minus. No, just positive 4. So the horizontal one is y equals negative 2. So no oblique then. You cannot have horizontal and oblique. Okay? So we have this vertical asymptote, and we have that horizontal asymptote, right? So there's really one thing that we can do. Think about this. I need to touch this point, I need to touch that point, and I need to do the whole asymptote thing. There's only one way to do that, right? There's only one option, really. Right? What about the other side? I have to go below, right? There are no more x-intercepts. I have to do that on the other side. The only thing is negative 1, negative 2, negative 3. My graph will have a hole in it right here because that point is not in the domain. So this would be the actual graph of that function. So there is a hole in there. Okay? I can actually find where that hole is by plugging negative 3 into the simplified version, because you can plug negative 3 in there. You don't get 0 in the denominator. So I'll just, to figure this out, it'll be negative 2 times negative 3 minus 5 over negative 3 minus 4. So what is that? Negative, I don't know, I lost count. So it's negative 11 over negative 7, so negative 11 over 7, right?
Negative 11 over negative 7.
Yeah, but they also have a minus in front. So, well, it was always there, right? They always had a minus there. So, yeah. So negative 11 over 7, that's what? That's still above negative 2, right? So it's still above the asymptote. So basically the whole story is you get a hole in there. Yeah. Well, if you're asked to do that, yes. But again, you have to, the big thing to realize that if your function simplifies, that does not affect the domain, but it does affect the vertical asymptotes. If something cancels out, that's no longer an asymptote. You don't get that asymptotic behavior when things kind of start flying off in different directions. You just get a hole in the graph. But the lines almost connect there. There's a little gap. Well, because that's the -3, because x was -3 at that point, right? Because I knew something funky happens at -3. That was the point. All right. Good? Good. All right. Okay, so that's basically section 4.5. So it took us a while to get through that one. That one is lengthy. But section 4.6, as I said, I can probably do it in one sentence now. Your book will not. Your book will spend good 10 pages on that section, but the whole theme. So section 4.6, there's a nonlinear inequalities. Okay? Nonlinear inequalities. So that means we know how to deal with linear inequalities. That's easy. You just solve it like an equation. You just have to remember to flip a sign sometimes. We dealt with that. We dealt with inequalities with absolute values. Those are also linear with absolute values. But this is a nonlinear. So things like, we haven't dealt with that yet, but if I do, x squared minus 4x, here's an example, minus 4x minus 12, let's say greater than or equal to 0. Okay? We cannot solve that algebraically. We cannot just start solving this as an equation or things like that. It will not happen. It will not help us to actually answer this question. But if we think about really what that question is asking, it's asking, well, for what values of x the expression on the left stays positive or 0, right? That's the question. From a graphical point of view, the question is, when is the graph of the expression on the left stays above the x-axis? Because if it's above the x-axis, that's when it's positive, right? So really, this whole thing comes down to graphing whatever the algebraic expression is. So if I look at this thing, and I just tell you, well, graph this. Graph x squared minus 4x minus 12. That's a quadratic polynomial, right? The way we graph polynomial functions is usually by factoring. So it's x minus 6, x plus 2, right? Those are the x-intercepts. And it's just going to be a parabola like that, right? You agree with that? That's roughly a sketch of that function. I just have to be really roughly sketching this function. I don't have to be anywhere near precision, right? It's a parabola that opens up. Those are the x-intercepts. So can you tell me for which values of x the graph of this function stays above the x-axis? So what x has to be in order for graph to be above the x-axis? So from -infinity to -6, right? Including -6 because of the equal part. Union from 2 to infinity. So you're just going to see when is it above the x-axis. If the question was less than 0, you would look below the x-axis, right? Does that make sense? If the question was greater than 5x minus 2, you'll just move everything to one side till you have 0 on one end, and then just kind of look at the graphs. Because basically, it's all going to be about your x-intercepts and your asymptotes and whether sign alternates or not. So it's really just coming down to sketching the graph really fast, and we know how to do that. Oh, you're right. So I had it flipped. Okay, I'll just do that. You're right. Sorry. Who cares? It's not that big of a, well, it's kind of a big deal, but my whole solution is wrong because of that, but very good catch. Okay? Sorry about that. So I should change that as well. Yeah, that would be the answer. Because again, you're just looking for the values of x that satisfy the inequality. So let me do something that has division maybe. So your book will really just, it will take you, it will make many, many steps if you just understand that it's just like graphing, okay? And you want to have 0 and 1 end, otherwise it won't work, okay? So your book goes through notion of defining a thing called critical number. And that's an important definition. Critical number. So those are your so those are numbers those are your x-intercepts and whatever's excluded from the domain, okay? So the things that make your function 0 or undefined. All right, so the critical number of a function is a number that make the function 0 or undefined. So zeros, the x-intercepts, and whatever is not in the domain. Because those are the places where the sign of the function can change. And that's the big thing. Remember how we talk about when the sign of the graph changes? It can only change at the x-intercept, so it crosses the x-axis, or at an asymptote where it flies in the opposite direction. Those are the only two instances where the sign changes of a function from positive to negative, from being above the x-axis to being below the x-axis. Okay? So this thing kind of, your book might ask you, hey, you find the critical numbers. Those are just x-intercepts and whatever's not in the domain. Okay? Now, in order to solve those inequalities, if you just understand how to sketch the quick graph and just look whether things are above the x-axis or below the x-axis. Okay? Here's an example. What was it? X cubed plus 2x squared. Was that the function we were playing with earlier? Yeah, minus 3x over x squared minus 5x minus 14, right? Let's do less than or equal to 0. Okay? Really, you just have to look at the graph and see where's the graph below the x-axis. So since we already did the graph of that function, that was funky, right? Was that the graph? All right. When is it below the x-axis? From negative infinity to negative 3. So it looks like it's below over here. Then when? Well, after negative 3 it goes positive, but then from negative 2, right, to 0, that's another interval where the graph is below the x-axis. And then from 1 to 7, right? That's when it's below the x-axis. Did you hear that? Now you have to be really careful to list our answer. So what are intervals? Since we just mentioned that, just looking at the graph, tell me, we went from negative infinity to negative 3. Negative 3 is an x-intercept, right? The function actually hits negative 3. So that's where the function equals 0, right? If I go back to the graph, that's the point where the function equals 0. So that should be in our solution, since our question one, what is this less than or equal to 0? So we're going to include negative 3. It's part of the solution, makes everything 0. Union, what was the other? From negative 2 to 0. But negative 2 is an asymptote, right? So I cannot include that in my solution because my function is undefined at that point. So I'll have a parenthesis at negative 2, but then I'll have a bracket at 0 because the function actually hits 0. So then I'll go from negative 2 to 0, not including -2, including 0. And then union again from 1 to 7, was it, right? Only including 1, because 1 is an x-intercept, but not including 7, because 7 is an asymptote. Okay? So basically, you will always have a parenthesis around asymptotes. X-intercepts, if your inequality says equal to, then you include those. If it's a strict inequality, you just put parentheses everywhere. Does that make sense? But it only works if you have 0 on one end. If you don't, then make sure you do. Just move everything to the one side. And you want this question to be, is it positive or negative? And then you can easily look at the graph. Okay? But does that make sense? Because if you just go through a quick sketch, then we don't have to talk about what your book talks about. The book goes crazy. They'll do this. They'll take a number line. They'll put all those critical numbers on it, which are x-intercepts and the asymptotes. And then it will test each interval by plugging numbers into the function to see is it positive, is it negative, and all that stuff. And I don't want to do that since we can sketch. We can sketch graphs, and this is the same thing. Now, I want to do one example that's a little funkier. And that's from your book. X minus 3 over x plus 4 greater than x plus 2 over x minus 5. Okay? So the first step in solving nonlinear inequalities is to get 0 on one end. I cannot do that. I mean, I cannot solve this inequality as it's written, because then I'll have to sketch the left side, the right side, and then look where they intersect, and when one is above the other, I'll just go crazy. It's easier just to compare everything to the x-axis. So the step 1, get 0 on one end. So it is x minus 3 over x plus 4 minus x plus 2 over x minus 5 greater than 0. That's the first step. Well, the second step, I really don't know how to graph this function on the left, because it's a difference of two functions. So what I actually have to do, I have to channel my, I actually have to do the subtraction. I actually have to subtract these two rational expressions. I have to subtract these two fractions. Okay, here's the page. Yeah. I have to subtract these two fractions to get it together. I have to get the common denominator and all that. You see, if this was an equation, then that's when you multiply both sides by the denominator and you cancel everything. You cannot do here, because denominator plays a huge role in inequalities. Because denominator gives us asymptotes, and the sign changes around asymptotes sometimes. So we need to keep track of the denominator. Okay? Why are you laughing? You don't get it? If this was an equation, you would just multiply both sides by the least common denominator. You would cancel all the denominators, because you only care about the x-intercepts. You don't care about the asymptotes when it's an equation. But when it's an equality, you care about asymptotes, because the sign changes at asymptotes, right? So you got to do the painful thing and actually combine them. So what is the least common denominator here? X plus 4, x minus 5. So that means you have to multiply the first one by x plus 4. I'm sorry. You have to multiply the first one by x minus 5, x minus 5. You have to multiply the second one by x plus 4, x plus 4, to add them together. Right? We're actually doing the good old addition of rational expressions. So x minus 3, x minus 5, x minus 3 minus x plus 2, x plus 4. Now I have to do a lot of foiling, and I have to do a lot of combining like terms and things like that, right? I actually have to do the math here. So FOIL, x minus 5 and x minus 3, are you going to have problems with that? You're just doing the FOIL? Say no? No. You should get x squared minus 8x plus 15 if you do your FOIL. Right? Yes. Thank you. I am sloppy. It's Monday. I'm always sloppy on Mondays. Right? If you FOIL right, that's what you should get. Now on the next one, you FOIL x plus 2 and x plus 4, and then you distribute the negative. You should get negative x squared minus 6x minus 8. Just check your work. You should be able to come up with that. I mean, you all know how to FOIL and distribute. So FOIL first, then distribute the negative. Is that okay? Did you get that? You should get that. I'm skipping a few steps, but I'm not teaching you how to FOIL in this class. And that should be appreciated. But I'm not. So x squared and x squared cancel. Combine like terms, negative 14x. Looks like plus 7 maybe. Yeah, because when it's factored, it's a lot easier when things are factored. Because then I see my asymptotes right away, right? I can also factor the numerator. I can pull out negative 7 to get it into 2x minus 1. I don't have to do that, but I just did, so I live with that. How is that? Is that okay? So, and now let's just do a quick sketch. Again, we just need a quick sketch. And your book will just do that. They'll even ignore the y-axis. Who cares? They're just going to go above, below. Who cares how high it goes? But if I do a quick sketch, the x-intercept would be when you set the numerator to 0. I'll get a sneeze. It's one of those that got stuck. Ooh. So, what is the x-intercept? 1/2, right? So we'll have an x-intercept at 1/2, somewhere here. Do you agree with that? Well, I just factored it because I could, right? Yeah, negative 7 doesn't play a role. You have to make 2x minus 1 equal 0. Okay. Hey, let's do it. It'll be easier. See, in my mind, it's easier if we actually grab this thing. Let's just grab this thing. Because look, we got 1/2 as an x-intercept, right? What will be the y-intercept? So we're going to set x equal to 0, right? So what do we get? 7 in the numerator. If x equals 0, we'll just get 7. In the denominator, we'll get 4 times negative 5. So that's negative 20. Right? So it's negative 7 over 20. No, again, 7 is not playing any role in that being equal to 0. 7 is 7. You just have to make sure that 2x minus 1 equals 0. And positive 1/2 makes 2x minus...
You could set the top one the same way, right?
Yeah. If I wanted to, negative 14x plus 7 equals 0, negative 14x equals negative 7, x equals 1/2. Right? You're going to get negative 7 is negative 7. Remember, if a product equals 0, then you have to be multiplying by 0. So what makes negative 7 0? Nothing. But what makes 2x minus 1 0? 1/2. So that's the only solution. Does that make sense? All right. So the y-intercept was negative 7 over 20. Who cares? Something tiny negative. Right? Now what are asymptotes? What are the vertical asymptotes of this? So negative 4 and 5. 1, 2, 3, 4, 5. right? What are the horizontal asymptotes? What about horizontal asymptote? Anyone? What? Your numerator is linear, your denominator is quadratic, isn't it? So what is the asymptote when it's linear over quadratic? What is the horizontal asymptote when it's a linear, degree 1, over quadratic? Yeah, 0, so y equals 0. Denominator is bigger, so how would you connect these 2 points? There's the only way to do that is something like that, right? There's the only way to connect those 2 intercepts and do the asymptote thing. Now, if we stick to our change the sign around odd multiplicities, it has to do that and that, right? From negative change to positive, from positive change to negative, because those things have multiplicities of 1, so signs change. Well, now the question was just strictly greater than 0, right? So now let's try to answer this question. The question was our function greater than 0, so it looks like from negative infinity to negative 4, right? Union from the x-intercept, which is 1/2, but not including 1/2 because that's strict inequality, all the way to the asymptote, which was 5. So from 1/2 to 5, and that's it. It's negative everywhere else. So that's it. That would be the solution. So if you do a quick sketch, then you're good. Yeah, that's what's above the x-axis. The one thing, when you do those sketches, you don't have to worry about the oblique asymptote. If you don't have a horizontal asymptote, then just keep sketching. Who cares what it does above the x-axis or below the x-axis? You only worry about when it changes the sign. And you can only change the sign at the x-intercepts and the asymptotes, vertical asymptotes. So if you have the numerator that's bigger than the denominator, then don't worry about don't do the division. Don't give me the oblique asymptote. That plays no role in the sign. Right? The oblique asymptote just kind of tells you what happens in the long run, so who cares? It's either going to stay above or below. It can only turn around and hit the x-axis at the intercept or jump over the x-axis at asymptote. And that's really the whole thing, when we're staying above the x-axis or below the x-axis. That makes sense? So if you do those quick sketches, just judge when it's above or below. And then use that multiplicity rule, which almost failed us earlier today, but luckily we were able to pull through and maintain it as a good rule. Okay, good. So that's the end of chapter 4. So your homework is still due on Wednesday. In the quiz. There's only one homework and one quiz.